By referring my YouTube video, graphs of trigonometric functions and inverse trigonometric functions, you can see that tan x where negative pi by 2 less than x less than pi by 2 is a one-to-one and on-to function, and it has the inverse given by arc tan x or tan inverse of x with the domain negative infinity less than x less than infinity. That is, the domain of arc tan x is the entire real line. The graph of the arc tan x is the mirror image of the graph of tan x about the line y equal to x. We now consider an example involving arc tan function. We show that v minus u by 1 plus v square less than tan inverse of u less than v minus u by 1 plus v square where 0 less than u less than v. And using this inequality, we also deduce that pi by 4 plus 3 by 25 less than tan inverse of 4 by 3 less than pi by 4 plus 1 by 6. We let f of x is equal to arc tan x or tan inverse of x, and also we take x in between u and v. F prime of x is equal to the derivative of arc tan function, that is equal to 1 by 1 plus x square. Now f is a continuous function, so Lagrange's mean value theorem can be applied. So there is a c in the open interval uv such that f of v minus f of u by v minus u is equal to f prime of c. Now what is f of v? F of v is tan inverse of v. F of u is tan inverse of u. So we get tan inverse of v minus tan inverse of u by v minus u is equal to 1 by 1 plus c square. We call it equation number 1. Our u less than c implies u square less than c square implies 1 plus u square less than 1 plus c square. So their reciprocals are related by the inequality 1 by 1 plus c square less than 1 by 1 plus u square. Hence from equation 1 we obtain tan inverse v minus tan inverse u all divided by v minus u is less than 1 by 1 plus u square. So that tan inverse v minus tan inverse u less than v minus u by 1 plus u square. Again c less than v implies c square less than v square implies 1 plus c square less than 1 plus v square. So that 1 by 1 plus c square greater than 1 by 1 plus v square. Therefore from equation 1 we obtain this inequality, which implies the inequality 3. Combining 2 and 3 we get the desired result. In this inequality we put v is equal to 4 by 3 and u is equal to 1. Substituting these values we get 3 by 25 less than tan inverse of 4 by 3 minus tan inverse of 1 less than 1 by 6. Tan inverse of 1 is pi by 4. So we have 3 by 25 plus pi by 4 less than tan inverse of 4 by 3 less than 1 by 6 plus pi by 4. As another example, using Lagrange's mean value theorem, we show that x by 1 plus x less than log of 1 plus x less than x when x greater than 0. We also show that 0 less than log of 1 plus x all inverse minus x inverse less than 1 for x greater than 0. For this purpose, we recall the another form of the statement of Lagrange's mean value theorem, which states that if f satisfies the two conditions in the Lagrange's mean value theorem, that f is continuous in the closed interval 0x, f is differentiable in the open interval 0x, then there exists theta 0 less than theta less than 1 such that f of x minus f of 0 by x minus 0 is equal to f prime of theta x. Here we consider f of x is equal to log of 1 plus x where x greater than 0. Then f of x satisfies the condition of Lagrange's mean value theorem in any interval of the form closed interval 0x. So there is a theta where 0 less than theta less than 1 such that f of x minus f of 0 by x minus 0 is equal to the derivative of f evaluated at theta x. Here theta x is a point in the open interval 0x because 0 less than theta less than 1. Now putting f of x is equal to log of 1 plus x, f of 0 is equal to log of 1 plus 0 is log 1 is 0. So the above simplifies to 1 by x times log of 1 plus x, which is equal to, see, derivative of log of 1 plus x is 1 upon 1 plus x. So f prime of theta x is obtained by putting theta x in place of x, and we obtain 1 by 1 plus theta x. Now 0 less than theta less than 1 and x greater than 0 implies theta x less than x. So 1 plus theta x strictly less than 1 plus x, so their reciprocals satisfies the inequality 1 by 1 plus theta x greater than 1 by 1 plus x. We have observed above that 1 by 1 plus theta x is 1 by x times log of 1 plus x. So we get that is greater than 1 by 1 plus x, and we call it equation number 1. Again 0 less than theta less than 1 and x greater than 0 implies theta x greater than 0, which implies 1 plus theta x greater than 1. So their reciprocals satisfies the inequality 1 by 1 plus theta x less than 1. So that what is 1 by 1 plus theta x? That is log of 1 plus x by x. So we obtain this is less than 1. So from 1 and 2 we obtain 1 by 1 plus x less than log of 1 plus x by x less than 1. So multiplying throughout by x, we get x by 1 plus x less than log of 1 plus x less than x, which implies taking reciprocals, inequality will get reversed. So we get the reciprocal of x by 1 plus x is 1 plus x by x greater than log of 1 plus x all inverse greater than 1 by x, which can be written as 1 by x plus 1 greater than log of 1 plus x all inverse greater than 1 by x, which implies 1 greater than log of 1 plus x all inverse minus x inverse greater than 0 as desired. As another example, we show that tan x by x greater than x by sin x when x lies in the interval open interval 0 pi by 2. See, it is equivalent to show that tan x by x minus x by sin x greater than 0 on this interval. By cross multiplying and simplifying, it can be seen that it is equivalent to show that tan x sin x minus x square by x sin x greater than 0 for 0 less than x less than pi by 2. We know that sin x is greater than 0 on the interval open interval 0 pi by 2. This can be observed by looking into the graph of sin x. So sin x greater than 0 on this interval, and x is also positive because 0 less than x. So if we multiply this sin x with x, we get x sin x. So x sin x also greater than 0 when 0 less than x less than pi by 2. So from this, in order to prove this, it is enough to prove that tan x sin x minus x square greater than 0 for 0 less than x less than pi by 2, because x sin x already greater than 0. So this quotient is greater than 0. It is enough to show that this numerator is greater than 0. Now for this purpose, we let f of x is equal to tan x sin x minus x square for 0 less than or equal to x less than pi by 2. Now we find that the derivative of f of x is sec square x sin x plus sin x. Why this step? we differentiate tan x sin x. The derivative of tan x is sec square x into sin x. Then we find the derivative of sin x. What is the derivative of sin x? Cos x. So tan x cos x, which gives sin x. And the derivative of x square is 2x, so we get minus 2x here. Now we differentiate f prime of x with respect to x. For that purpose, we note that the derivative of sec square x is, we put sec x is equal to u, so that this becomes d by dx of u square, which is equal to d by du of u square times du by dx, chain rule, which is equal to 2u sec x tan x, because u is sec x, its derivative is sec x tan x. Now substitute u, which is sec x. So we ultimately get 2 sec square x tan x. So second derivative of f of x is sec square x cos x plus sin x into 2 sec square x tan x plus cos x minus 2, which on simplification gives sec x plus cos x minus 2 plus 2 sin x tan x sec square x. Now sec x plus cos x minus 2 can be expressed as the square of this square root of sec x minus square root of cos x whole square. Being the square of a non-zero number, this value will be strictly greater than 0. And also on the interval, open interval 0 pi by 2, sin x is greater than 0, tan x is greater than 0, and sec square x also greater than 0, because square of non-zero number is always greater than 0. So we conclude that f double prime of x strictly greater than 0 for 0 less than x less than pi by 2. Also f second derivative evaluated at 0 is equal to sec square 0 cos 0 plus sin 0 into 2 sec square 0 tan 0 plus cos 0 minus 2, and putting all these values we get this is equal to 0. Now f double prime of x is greater than 0 for 0 less than x less than pi by 2. F double prime of 0 is equal to 0, showing that the function f prime is strictly increasing in left closed right open interval 0 pi by 2, because of the property that second derivative greater than 0 on this open interval, and the second derivative is equal to 0 when x is equal to 0. We can see that the derivative f derivative is strictly increasing. Also f prime of 0 is equal to 0. Okay, so if we take x greater than 0, then what happens? Because f prime is strictly increasing, we can say that f prime of x strictly greater than f prime of 0. What is f prime of 0? F prime of 0 is 0. So we get f prime of x greater than 0 for 0 less than x less than pi by 2. F prime of x greater than 0 for 0 less than x less than pi by 2, and also f prime of 0 is equal to 0. So we can say that f is strictly increasing in the left closed right open interval 0 pi by 2. Also f of 0 is equal to 0. Okay, so x greater than 0 or 0 less than x implies f of x greater than f of 0, because f is strictly increasing in left closed right open interval 0 pi by 2. Now what about f of 0? F of 0 is 0. See, we have f of x greater than 0 for 0 less than x less than pi by 2. Now f of x is tan x sin x minus x square. So we get this inequality. X sin x is a positive quantity, so we divide this inequality with the x sin x, and it doesn't affect the sign. So we get this is greater than 0 for 0 less than x less than pi by 2. Now this is nothing but tan x by x greater than x sin x for 0 less than x less than pi by 2. As another example, we show that 2 by pi less than sin x by x less than 1 when 0 less than x less than pi by 2. For this purpose, we consider the function f of x is equal to sin x by x when x not equal to 0, and f of x is equal to 1 when x is equal to 0. See, sin x by x is not defined at x is equal to 0 because of the presence of x in the denominator. The graph of f of x is given here. F is continuous in closed interval 0 pi by 2 and differentiable on open interval 0 pi by 2. Its derivative on the open interval 0 pi by 2 is given by f prime of x is equal to x cos x minus sin x by x square. This can be obtained using quotient rule, applying quotient rule. This can be obtained by applying quotient rule to the function sin x by x. We let capital F of x is equal to x cos x minus sin x, where x belongs to closed interval 0 pi by 2. We consider this function to check the behavior of f prime of x. X square is always positive on the interval open interval 0 pi by 2. So we need to check the behavior of x cos x minus sin x. That is the reason why we choose capital F of x is equal to x cos x minus sin x here. Now f prime of x is equal to, by differentiating here, this is we have to apply product rule. We obtain cos x minus x sin x. Derivative of sin x is cos x, so we get minus cos x here. So this is equal to minus x sin x, and on the interval 0 pi by 2, x is positive and sin x is positive. So x sin x is positive. So negative x sin x will be less than 0. Also f prime of 0 is equal to cos 0 minus 0 sin 0 minus cos 0, which is equal to 1 minus 0 minus 1, which is equal to 0. Now f prime of x less than 0 on the interval open interval 0 pi by 2. F prime of 0 is equal to 0. So the function f is strictly decreasing on left closed right open interval 0 pi by 2. So if we choose x belongs to open interval 0 pi by 2, then x greater than 0, f is decreasing, so that f of x less than f of 0. What is f of 0? F of 0 is 0 from here. So we get capital F of x less than 0 on x belongs to open interval 0 pi by 2. What is capital F of x? X cos x minus sin x. So x cos x minus sin x less than 0 for x belongs to open interval 0 pi by 2. Now we divide this inequality by x square, which is positive. So inequality will not be affected. So we obtain x cos x minus sin x by x square less than 0 for x belongs to open interval 0 pi by 2. Now what is this? This is f prime of x, already seen. So this is f prime of x, and we have f prime of x less than 0 for x belongs to open interval 0 pi by 2. Hence f is strictly decreasing on open interval 0 pi by 2. This implies that when 0 less than x less than pi by 2, f of 0 greater than f of x greater than f of pi by 2, because f is strictly decreasing. So 0 less than x less than pi by 2 gives this inequalities. By the definition of f of 0 is 1, f of x is sin x by x, and f of pi by 2 is sin pi by 2 by pi by 2. What is that? 1 by pi by 2. So this gives this inequality.